Thanks for being here. I'm Nomeli. I want to share one of my client stories with you about GANs in Diagnostic, Predictive, and Prescriptive Analytics. GANs are one of the hottest topics in deep learning these days. What is special about these networks? They are able to learn how to produce data from a data set, which is indistinguishable from the original data. That sounds crazy, right? Who I am, I'm manager with Accenture Digital, based out of San Francisco office, and also leading the resources and people growth and development. Before Accenture, I used to be an assistant research professor at the University of Maryland and also a joint faculty at George Mason University. GANs for data augmentations. What is adversarial example? It is an instance with a small and intentional feature perturbations that would cause deep learning models to make false predictions. Why are we interested in GANs? Because they help us to find the loopholes of machine learning and deep learning models. And we can, instead of attacking deep neural networks, protecting them from being attacked. I'm going to give you a couple of applications, give you a couple of examples about the applications of GANs. Imagine, a self-driving car crashes into another car because it ignores the stop sign. Somebody had placed or drawn something over the sign, which still looks like a stop sign to human beings, with a little bit dirt. But it was designed to look like a different sign for the sign recognition software of the car. Another example, spam detector has failed to classify an email as a spam because that email has been designed to resemble a normal email, but with the intention of cheating the recipient. Another example, at the airport, the AI-powered scanners scans suitcases for weapons. But what if a knife was developed to avoid the detection by making the deep neural networks think it's a knife? Let's see it. This is a knife. Of course, you don't want to be on that plane. So the adversarial examples for images are images, again, with intention to deceive deep neural networks. These examples impressively demonstrate how easily deep neural networks can be deceived by these images that appear harmless to humans. These changes in predictions are incomprehensible for human observer. So let's consider these examples, the adversarial examples, as optical illusions for machines. Before getting to the client story, I want to briefly give you an introduction about GANs and the techniques and goals. There are many ways to create adversarial example. Most approaches suggest minimizing the distance between the adversarial examples and the instance to be manipulated, while shifting the outcome prediction toward the desired target, which is going to be adversarial. There are several methods, as I said. Some of the methods require access to the gradient base of the model, which makes them only applicable to gradient-based models such as deep neural networks. But there are some other methods that require access only to prediction function, which makes those methods model agnostic. There are two techniques. A white box technique assumes the adversary has full knowledge and access to the model, underlying architecture, inputs, outputs, and weights. But the black box technique assumes the adversary only has access to the inputs and outputs and knows nothing about the underlying architecture and weights. There are also two types of goals. A misclassification assumes that the adversary only wants the outcome classification to be wrong. An image of a cat to be classified any other animals, dog, puppy, zebra. But source target misclassification assumes the adversary not only wants a specific instance from a specific source to be classified as a specific target, a stop sign to be classified as a start sign, which could cause the self-driving car crash into another car. Don't worry about the equations. I'm just gonna say here, this is remarkably powerful. This technique is remarkably powerful and yet intuitive. It is designed to attack deep neural networks by leveraging the way they learn, gradients. And this is the way we can change the gradients toward the desired direction that could cause deep learning models to make false predictions. And I'm going to give credits to Ian Goodflow and his doctoral advisor, Yoshua Bengio. In 2014, they published the first article about GANs. On the left-hand side, you see a picture depicting the variation of the prediction accuracy with respect to perturbations. As you can see, the accuracy decreases with perturbations. On the first row, there is no perturbations. And as you can see, the actual is equal to the predicted. 5 has, on the top left, 5 has been classified as 5, 2 has been labeled as 2. But by adding small perturbations to the deep neural network, to the images, deep neural network made false predictions. 7 has been classified as 3. Again, these images appear harmless to human, and these are the optical illusions for machines only. How we can stop this from happening? If we could generate all the possible attacks, which is difficult, we could protect our deep neural networks and also increase the accuracy of the model whenever we deal with limited data sets. CNN, convolutional neural networks, are invariant to transformations, rotation, scale, and all general affine transformations, if we don't use max pooling for them. But we can do all of the transformation, and we can also use GANs for creating different images and do the data augmentations before training the model on a limited data sets. Machine learning is all about balancing between problem complexity, model complexity, data size, and accuracy. You cannot tackle a complex problem with a simple model. In order to use a simple model and train the complex model to attack a complex problem, you need sufficient number and amount of data to train the model on. But what if we are lacking data? We could use GANs for data augmentation. Another application, a self-driving car, did a poor job on object detection in foggy weather because we had limited number of images captured during the foggy weather. So what we did, we used the original image, we downloaded foggy images from internet, combined them together to create this one. We need to be careful here. It's not that easy. When you're artificially synthesizing the data, you just be cautious and bear in mind whether or not you might be accidentally simulating the tiny subset of the space of all possible examples. What would happen? You make your model biased towards specific images. You can increase the accuracy of the prediction, but you may the model may do a poor job in real-world applications. On those images, against those images the model hasn't seen during the training. Client story starts from here. One of our clients came to us and they asked for help of pattern detection. They experienced outages in their production line. whenever the outage occurs due to the broken equipment, it's very costly and time-consuming to first detect that broken equipment and then fix it. They installed around 300 sensors all over the places in the production line and started collecting data. When they asked us for help, they were lacking data. And we didn't have enough number of instances to train the model. So the main two asks here are detecting the stoppage pattern and then identifying the most impactful sensors in the production line for that specific industry. This is the whole overview. We started from data pre-processing. We use GANs for augmenting the data. We use mutual information and artificial intelligence to detect the stoppage pattern for them and then generate the feature importance list and rank the sensors based on their impacts on the model. Okay, what you're looking at is a 14 consecutive day of cross-correlation between 286 sensors, and the outage occurred somewhere in between. Just guess which pattern looks like anomalous to you. Just guess. 2. Any other guess? 9? 7? Okay, now let's see. The outage occurred in day 5. So based on this experience, now guess, this is another outage. Where the outage occurs, which one looks like to be an anomalous pattern? 11? 12 and 11. 15. One more. 9. You were right. So the outage occurred on day 11. But cross-correlation cannot do a good job in detecting the stoppage pattern, because cross-correlation only captures the linear relationship between the sensors. This is a very complex and non-linear problem. We need a more complex model to detect the stoppage pattern. So this time we are using mutual information, which can capture both linear and non-linear relationships between the sensors. And now to you, which pattern looks like abnormal? This is a different outage. So, 10, 13, 15, 7, not correct, none of them. 16, no. 20. So the outage occurred here. As you can see, the intensity of the color is different from the other ones. Now, based on this experience, what about here? 5, you got it. Yay. So the outage occurred here. So mutual information could successfully detect the stoppage pattern, because it, again, captures both linear and non-linear relationship between the sensors. So we generate the operating dashboard for the client, including 286 sensors. This picture depicts the variation of rotor speed with respect to time. Whenever the outage occurs, they need to shut down the whole process. Again, it costs them a lot of money to bring back the system up and running. But monitoring 286 sensors at the same time is very difficult with unarmed eyes. So we didn't stop here. We went actually to down select the most important sensors by basically using descriptive analytics and predictive analytics. We compare the data distribution with a normal distribution. This is a QQ plot. If the data comes from the normal distribution, the blue dots should lie on the straight line. And we also use other techniques to detect the extreme values, and also PCA and cross-correlation to basically do the dimensionality reduction. The engineers from the client side create a list of most impactful sensors. We also created another list independent of each other. And when we merged those lists, we found 5 sensors. So we let the data to speak for itself without any engineering and SME knowledge. 5 sensors were in the list of engineers. When they look at those sensors, they're like, oh, we totally forgot about those sensors, and they are really important. So by combining the physics-based model and machine learning models, we could successfully down-select the most influential sensors. So we generated another dashboard, only 55 sensors now, 60-second animations. Outage occurs in the middle of this animation. And whenever the outage occurs, the mutual information between these important sensors goes to nearly 0. So whenever you see the pixel intensity, the high pixel intensity of blue and navy blue, you will see that the outage occurred on that day. It's getting there, right here. And it remains the same for a couple of days. And then after a couple of days or weeks, they bring back the system up and running, and those navy blue will disappear. And again, white and yellow stands for the high mutual information. And they brought back the system up and running. This is about the pattern detection. We didn't stop here. We wanted more. And we use ensemble methods, machine learning techniques, and also voting classifier, including both ensemble methods, random forest gradient boosting, deep neural networks, and also regularized machine learning algorithm, Ridge and Lasso, for feature selection. And we generate the feature importance list for them by ranking them. So instead of, again, 55 sensors, we can only take care of the top 5 or top 10 in order to prevent the outages from happening. In conclusions, we use GANs for augmenting the data. We use mutual information for established pattern detection. And we also help them in predictive maintenance by identifying the most impactful features in their industry. Thank you.